Welcome, everybody. Before we start, let me tell you a little bit about myself and the context in which I've been looking at some of these interesting technologies. My name's Holly Cummins. I'm an IBMer. I've been with IBM for a long time. And in most of my career in IBM, I've worked in one way or another in the WebSphere organization. Sometimes things at the top of the stack, sometimes things nearer the bottom of the stack, but mostly to do with WebSphere. What I'm currently working on is the WebSphere Liberty profile, which is something that we're incredibly proud of. I think it's a really nice piece of engineering, so I'm excited to have been involved with that. I've also done other non-IBM things, so I'm an Apache committer, and in particular, I'm a committer on the Apache Aries project, which has to do with enterprise OSGI and making OSGI work with some of the JEE specifications that we quite like using. So if you'd like to know more about enterprise OSGI, I have written a book, so it's there, but that's the last I'll say on that subject. Before we talk about the future and some of the interesting things that are going on with IoT, I want to give a bit of context about where we've come from, because it's kind of staggering how much the world has changed just in a generation or two. So in 1949, Popular Mechanics said computers in the future may weigh no more than 1.5 tons. You know, and it was amazing. It could be as small as a car. And Thomas Watson said, I think there's a world market for maybe 5 computers. And compared to now, where usually I have 5 computers in my bag at any one time without even really thinking about it. And it's easy to laugh at this prediction, but as an IBMer, I do feel compelled to point out that he was right for about 10 years. And most of us, if we made a prediction that was true for 10 years, we'd be like, yes, I'm awesome, I'm such a technical visionary. So we shouldn't laugh too much. But, you know, it really does highlight that there's such a difference between how computers were then and how they are now. So, you know, then, if you were in the same room with a computer, you knew about it because the computer filled most of the room. Whereas now we have this much more ubiquitous model of computing where computers are absolutely everywhere. And so there's the computers that I know about, like my laptop, but then I'm surrounded by a lot of computers that I don't even really register as computers. So I knew it was sort of the dawn of the machine age when a few years ago I got a new fridge and the fridge had a computer in it. And this would have been fine, except that the fridge and I disagreed about what the fridge should do. And what the fridge thought the fridge should do was beep for 6 hours every night while I was trying to sleep. And so, you know, there was a battle with the computer and, you know, replacing of software and replacing of hardware and that kind of thing. And in the end, it's hard to say who won. I think we both lost because the fridge went back to the manufacturer and I got a different fridge. So that was the end of my experience with computerized fridges. One thing about that fridge was that there was a computer in the fridge, but it wasn't connected to anything. You know, there was no way of me going to my web browser and saying, "Fridge, I'd like you to stop beeping." That would be, you know, that's the behavior I'd like from my fridge. You know, so it was a very isolated computer. And we talk about these models where, you know, the fridge is more connected to the internet, so that the fridge, you know, it emails you to say, by the way, perhaps you want to add this to your avocado list because you're running low on ketchup. Or it emails you at the end of the day and says, oh, you better have fish and chips tonight because, you know, it's about to go off. And this model where instead of being left to its own devices, the fridge is much more connected. And this is something that we've been talking about for a while, and we haven't really got there yet. We're getting closer, but it's still very much on the horizon. So why is it interesting what my fridge does? Well, there's a couple of reasons. So the first is that it's an absolutely phenomenal business opportunity. The number of devices that's going to be out there is so big, and each of them is going to need a software engineer to write some software for them. It's going to need engineers to maintain them and design them. And so that's a lot of money and a lot of really new business opportunities. But there's another reason as well, which is that it's so much fun. So I've talked a couple of times on IoT, and usually I have a sense when I do so that most of the people there, even though I'm at a tech conference and, our employers are probably paying for us to be here, that this is a spare time thing. And certainly that's how it is for me. So I'll do a quick straw poll. How many of you have a business interest in IoT, a work interest? There's not a single hand in the room. Okay, so how many of you have sort of a personal hobbyist interest? I'm relieved to see hands go up, and I'm relieved to see most of the hands go up, because otherwise that would mean you were sat here going, actually, I don't have any interest in IoT. I wish you'd stop talking and let me get to lunch. So, this is very much a hobbyist thing. And shh, I won't tell if you won't tell, because, yeah. So let's try and make these metrics a bit more rigorous in a while. I do feel compelled, even though it's a hobbyist interest for me and it's a hobbyist interest for you, to put a couple of slides in on how we do deal with IoT in a professional context. And if we do come away from this and we say, well, that so far this is hobbyist, but actually I can see that this is going to be something that's really interesting to my work. I have a top tip for you. So the first tip is that my experience in doing it is every time I write something, I type IoT, and autocorrect changes it to JOT. And this drives me absolutely bonkers. And I put up with it for about a year, and then it finally occurred to me that I could fix the problem. So step one, it's such a little thing, but this is my top tip. This is the thing that you will thank me for most if you do end up doing any writing about IoT, is take the 10 seconds to edit your dictionary to correct it. The one reason to leave it as JOT is that someone pointed out that if IoT is Internet of Things, then JOT is Ginternet of Things. And I think we can all get behind the Ginternet of Things. So the second step, which is the more obvious one, is to get yourself some hardware. And this can be sort of a confusing area. It can take a while to get your head around all the available options. The basic division that you're looking at is between a microcontroller and a microprocessor. And it took me a while to figure out what the difference was, because they're both sort of computers and they both have micro in the name. Well, the way I like to think of it is that a microcontroller is sort of a computer. So it can do a lot of things that computers can do. It can run a C program, probably. It can connect to the internet. You can program it, but you're not going to run an operating system on it. Whereas a microprocessor is really a computer. A microprocessor, as far as you're concerned, is indistinguishable from something like a laptop or a server in terms of the programs that you can run on it. You may find it's got a little bit less power, you may find it's got some wrinkles, but essentially you can treat it in the same way as you would any computer. So for microcontrollers, there's quite a few options. So I don't know if you've heard the expression that no presentation is complete without a picture of a cat. So I see your cat, and I raise you a bunny, a bird, and a snake. So the starting point for microcontrollers is a processor called a PIC, and it's really popular, and it's only £2, which is incredibly cheap. But how many of you have heard of PIC? Yeah, just one or two. And I think this is where PIC has a lot of things going for it. But it's also got some disadvantages because it's not accessible in the way that some of its successors were. So PIC, I think you have to be somewhat hardcore to get into. But that really changed. So we've got things like the Arduino. That's a lot more money than a PIC. So it's about 25 times more expensive, but it's a really inviting system to program on. But the one that's really revolutionized this market, and I think made it a lot more accessible to people like you and I, is the Arduino. And that's pretty cheap. It's £23. It's not a lot of money. And it provides an IDE, and it provides a lot of support and ecosystem that make it possible to have a play. £23 is pretty cheap, but it's also kind of expensive compared to something like the PIC. And so one of the nice things about Arduino is it's open as well. So there's a huge range of Arduino compatible processors, and those are about half the price. So those are really worth looking at as well. So here we have the Arduino. What it's got is £23. You'd assume that it would have an Ethernet connector, but actually, sadly, it doesn't. And that is a real barrier when doing Internet of Things because you haven't got the internet. It hasn't got Wi-Fi, so it's not like it's missing Ethernet, but does have Wi-Fi instead. So for Internet of Things, we're kind of left with just things instead. So that is a limitation. It's possible, it's completely possible to connect an Arduino to the internet, of course, lots of people do, but you have to kind of think about what the best way is. So you can buy what's called a Shield, and this is basically a daughter board for the Arduino. So these pins connect to the Arduino, and then it gives you Ethernet. But that's £10, which is kind of a drag, because you've almost doubled the cost of the board, potentially, just to get it to talk to the internet. You can buy, if you're going to pay that much, you could pay more and connect it by Wi-Fi, but then you're talking really a lot of money. One thing that a lot of people do is they use a Raspberry Pi to connect the Arduino to the internet. And this is because the Raspberry Pi, despite being a full computer, is actually cheaper than just a Wi-Fi shield for the Arduino. And it's even cheaper than that, really, because although if you were to go out and buy a Raspberry Pi, it would be £25, I think almost everyone has at least one Raspberry Pi in their sock drawer. And so if you just take that Raspberry Pi that you already have and connect it to the Arduino, then you're connected to the internet and you're sorted. So certainly that's what the pattern that I've used for a long time. But that does have some problems as well. And one of them has to do with limitations of the Raspberry Pi. So the Raspberry Pi is such an amazing project, and they've done such wonderful things with it. I think the one thing where maybe they didn't succeed as much as they hoped to was they really intended it as an educational tool. And I think it's a bit like how we're at a professional conference, but most of us are hobbyists with the Raspberry Pi. I think that audience is the audience who are mostly driving the demand for it rather than schools. But that's a sense. I don't have firm evidence for that. Because it's so cheap, the Raspberry Pi, the CPU is not very powerful, it's a bit old, it's a bit cheap. It doesn't have onboard storage, so you use a micro SD card. The RAM's pretty limited, 512 meg probably, depending on your model. The USB is also very limited, and this has caused me a lot of problems when I've been working with it. So you've got, on the new ones you've got 4, but here you've got 2 USB ports. But they fight. And so if you have, one model I've used is I've used a Wi-Fi dongle on the Raspberry Pi to connect it to the internet. And then I've had it connected via USB to the Arduino. And unfortunately, it meant that I had to choose at any particular moment whether I wanted to do Wi-Fi or talk to the Arduino. I couldn't do both. And so I had a system where I had sensors and they wanted to upload data to the internet. And I had to really throttle back how much I could upload because otherwise it just didn't work. So that did seem non-ideal in that system. The other thing about the Raspberry Pi is that we think of it as just sort of an interface for the Arduino, but it does actually have GPIO pins of its own, so you can use it without an Arduino. But because there's no analog pins, they're kind of limited, and I think the much more usual pattern is Raspberry Pi plus Arduino. A couple of months ago, they've come out with a new model, which is a lot more powerful. So it removes some of the limitations. So it's got this quad-core 900 megahertz CPU, which is kind of cool, but it keeps a lot of the same limitations. So it's still got SD storage. And I've found that the Raspberry Pi is incredibly slow. And I think part of that is the CPU, but I think a big part of it is the storage as well, because SD storage compared to an SSD drive is going to be about 10 times, a tenth the speed. And so many applications are really I/O and disk I/O intensive, and that does kind of drag down the performance, even if you've got 4 cores. There's more RAM, but again, I'm not sure that RAM is the performance limitation. It's got more USB ports, but I'm not sure whether quantity was the issue with the USB. There have been a lot of competitors to the Raspberry Pi. A lot of them overcome some of the limitations or make different trade-offs. So the BeagleBone Black is really popular. It's a bit more money, but it's got a more powerful CPU, and it's also got the microcontrollers on board, unlike the Raspberry Pi. It's got onboard flash storage as well. And it has an Ethernet connector, which is kind of cool. Arduino are getting into this model as well, so they're moving into microprocessors as well as microcontrollers. Like the BeagleBone, it's got a microcontroller and a microprocessor on board. You've got Ethernet, you've got onboard Wi-Fi, which is kind of good. Another option in this area is the pcDuino. And what the pcDuino have done is they've upped the price a little bit more, but it's still pretty reasonable, really, because it's £60, and that's for a dual-core computer. It's got 4 gig of flash. It's got 1 gig of RAM, so it's a pretty solid specification. You know, this is better than a desktop from a few years ago. And they've done an interesting thing with the pins, which is that they've taken advantage of the fact that Arduino is an open specification, and they've got what they call Arduino-ish pins. And what that means is that the pin layout is the same, but that if you try to use devices, they may work or they may not. So I found a lot of my sensors, I had to really recalibrate them when I started using them with the pcDuino instead of using them with the Arduino, because they just worked in a slightly different way and the voltages were a little bit different and that kind of thing. So I decided to try the pcDuino because I found the Raspberry Pi kind of limited, and it was a slightly tougher transition than I'd expected. But the pcDuino, it does have a lot of attractions. So again, it's got onboard Wi-Fi. And the other thing that I really found appealing is that it's got a battery connector. And so with the Raspberry Pi, we think of it as, you know, this amazing compact device, and you could use it for sort of wearable applications. But when you use it for a wearable application, you find that you have to stay plugged in, and so it's not really very wearable at all. Whereas the pcDuino seems much more optimized for a model where maybe you're going to take this compact device and you're actually going to use it in a mobile way. But there is a story of woe with the battery, which is that I bought my pcDuino and I was really excited, and I did some research and it said it has a JST connector. So I thought, right. And so I did more research and I found that most embeddable batteries have JST connectors, and so I thought, right, aren't I clever? I have used the internet, I have purchased the correct things. But I don't know if you can see, I found it difficult to photograph. So that is a 2-pin connector, which is quite large. And that is a 5-pin connector, which is quite small. And these things just weren't compatible at all, which I think was one of those things that to people who know this area, they would have said, well, of course JST-PH isn't compatible with JST-SH, obviously. But I'd been naive and I'd looked at the 3 letters and assumed that there was going to be some interoperability because there was going to be, you know, standardization, and why would you put a battery connector that didn't connect to popular batteries? Well, it turns out that that's exactly what they've done. So I found this on the internet well after I had purchased all my batteries and all my connectors. And I sort of thought, why? Why would you do that? Why would you put a battery connector on that doesn't adhere to the standards in force? I'm sure there are very good technical reasons for them, but from my outsider's perspective, I was kind of surprised at the lack of standardization in this area. But I did get there. It wasn't as easy as I'd hoped, but I did get there. So you can see this is the revised photo. So you can see I have my battery with 2 cables coming out of it, and I have my battery connector with 5 cables coming out of it. And then somewhere up there, I have all of the cables that aren't connected to anything, and I've got the soldering, and I've got the very attractive joins covered with electrical tape, and I've got the electrical tape here to try and prevent battery strain. And so this worked. You can see, look, there's glowing light. There is no power, and there is glowing lights. So I was incredibly pleased with this until I discovered that the battery didn't seem to give as much voltage as a wired connection still. So I'll come on to this. But there are LEDs here. And it turns out that LEDs need more power than the battery provides. And again, I think, why? How did this get standardized in this way? So why bother at all at this point? Because I've spent quite a lot of time, and I've had to cut lots of things and solder them together, and what's the point? Well, something like the pcDuino is kind of amazing, because for the price, you've got so much power. And the folks at Arduino were saying that their new microcontrollers have more power than their microprocessors from a few years ago. So the speed at which these devices are getting enough muscle to compete with laptops is kind of amazing. And so this means a couple of things. It means, obviously, you can do a lot more with these boards. But there's another way of thinking about it as well, which is that you can know less. A few months ago, I did a webinar with Vaden, and they did an IoT webinar. And of course, I'd left it to the last minute. And so I was flying out to Finland at stupid o'clock on Monday morning, and it was about 9 o'clock on Sunday night. And I was like, right, I'm going to start my IoT demo. And then I realized that I had quite a lot of work to do. And I was going to use MQTT. And there's loads of libraries for MQTT in lots of languages, including C. And I thought, well, the C seems to be the appropriate language to do my interfacing in, so I'll do it in C. And so I started to write. And then about half an hour in, I remembered that I haven't done C for 20 years, and that C is actually kind of hard, especially if you haven't done it for 20 years. And so I looked at this and I said, all I was doing was something that would just read the sensor and then just send it to the C MQTT protocol. So it wasn't hard, but it was too hard for me at 9 o'clock on a Sunday night. So what I did instead was I wrote something in Java. So every time the machine boots, it fires up a Java client, and all that Java does is read the value from a sensor and use the MQTT library. And so I think proper embedded people, luckily I know there's none in the room, so it's okay, but proper embedded people, if they see that, they'd just be going, what? Why? Rolling in their graves, because it's such a heavyweight way of doing something that was actually quite simple. But for me, actually, it was the most lightweight way, because if I'd done it in C, I would have had to spend a day reminding myself how to program C. And as it was, I was able to do it really efficiently. And so I like to think, I kind of feel like I have to turn in my geek card, and I'm kind of ashamed of the whole episode. But on the other hand, I think actually, no, it's really kind of cool that these devices have transformed enough that now someone who's a software engineer, and I know a lot about JEE, and I know a lot about lots of things, it's just that C isn't one of my specialties, and I can still do something kind of interesting. So, in other words, I'm not dumb, honest, I just don't know C anymore. So this power does come with a cost, though. So with great power comes moderate cost. And there are reasons that maybe, even though a pcDuino can do all of these things and a Raspberry Pi can do all of these things, you still want something a bit less beefy for your embedded project. So one, of course, is cost. So a Raspberry Pi is £30. That's kind of cheap and kind of awesome compared to a laptop. But compared to a £2 PIC controller, it's a lot of money. And if you're going to do something commercial with this, then you're going to choose the £2 PIC controller over something like an Arduino, because when you do one, £30 is fine. When you do several thousand of them, £30 starts to become pretty prohibitive. Another issue is size. So the pcDuinos and the Raspberry Pis, they're pretty compact. It's impressive, but they're kind of phone-sized rather than stamp-sized. So for some applications, that's just not going to cut it. And a related issue as well has to do with, so this, I have to apologize for the illustration. This is supposed to be a power brick. And what I'm trying to represent here is the fact that these more powerful devices do draw a lot more power. And so then that means that batteries and that kind of thing create an extra challenge, because you need a bigger, more expensive battery. So all of that's kind of reasons to say, actually, you know what? I'm not going to do a microprocessor. I'm just going to stick with the microcontroller, because I don't need to do very much. But on the other hand, the microcontrollers do give you this really cool opportunity, which is that you can use exactly the same skills you use in your day job to do IoT things. So you can have an application server, which is kind of awesome. And what the application server brings you is it brings you JEE, and I think Java EE is kind of a bit of a dirty word now, and we're all so over that, and we've never really recovered from JEE too. But actually, when we think about what comes with JEE, a lot of these things are incredibly useful, and we probably do use them every day. So things like servlets, things like CDI, that's just so useful, and being able to use these programming models is really handy. The code for my demo I think some demo code, you sort of say, yep, I'm going to put this up on GitHub, and I'm going to share it, and it's going to be really useful. The code for that demo, I am never, ever, ever sharing. It is the worst code, because again, I sort of hacked it together in a screaming hurry, and I cut and paste code from everywhere. And so it has every programming model in it. So it's got, it's got JEE, it's got, it's got REST, it's got CDI, it's got JPA. It's using all of them in the most inefficient way possible. So don't expect sample code. But again, it was kind of cool that I was able to do it, and I didn't have to worry about the performance characteristics too much. So again, I thought, I need to get something out of a web page. Let's bring in REST. So I just brought in REST, and it just worked, and that was kind of cool. One thing I haven't got in there at the moment is WebSockets. But if I'd wanted to, I could have, and that would have been cool. And so this does bring us to this sort of new model of computing, where not only do we have computers in all of our devices, these computers are potentially incredibly powerful and incredibly familiar to us from the application layer. So this is my vision of the future, which is that not only does my fridge have a computer in it, but the fridge is running WebSphere, and the car is running WebSphere, and the washing machine is running WebSphere. I don't think that's the official IBM line, by the way. And the thing that makes this possible, because I think probably when a lot of us think WebSphere, we don't necessarily think, the ideal candidate to embed into a refrigerator. How many of you have heard of the Liberty profile? One hand. So I think if you think you know WebSphere, but you haven't tried Liberty, then you kind of need to think again, because we've done some really kind of amazing things with it. How many of you were in Mark Reinhold's talk yesterday? A handful. He was talking about the modularization in Java 9. And we've been on a really similar journey with WebSphere. And so we took something that was very powerful, but was kind of monolithic, and we modularized it. And that gave us a lot of benefits. So it became really fast. So it starts in under 5 seconds. I think it's about 3 seconds on a decent laptop. But it's so lightweight, so the download is like 50 meg, and then you just download it and you unzip it. I should say as well, by the way, I'm not here to sell Liberty, partly because it's free for developers and free for small-scale production, but I do work on it, and I'm really proud of what we've done, which is why I have slides on it, and also it powers the demo. And the thing that enables this lightweightness and speed is that it's totally modular, so you only use what you need. And so if you can, instead of having, we've just announced JEE 7 support, but you don't have to take all of JEE 7 in your application server and have it all in memory and have it all in disk. You can just take the bits that you need. And finally, it starts in 3 seconds, which is kind of cool, but you actually almost never need to restart it because it's totally dynamic. So you change the config, and then it just says, I see you're now using CDI. Let me load that up, which is kind of cool. And the technology that enables all of this is OSGI. And so we've got so much out of OSGI. It's absolutely transformed the characteristics of our product, both in terms of modularity and dynamism. And as I said, it's free for small-scale production, and the limit is that you can use up to 2 gigs of RAM per organization. So for some organizations, this is going to be a pretty small limit, but for IoT, it's actually a huge limit, because if you assume 100 megabytes per Raspberry Pi, that means you could have 20 Raspberry Pis, and it would still be free. I don't know whether you'd actually want 20 Raspberry Pis, but the possibility is there. And there's an interesting synchronicity here, because when we set out to write Liberty, our target audience was really developers, and we thought we were going to make a runtime that's absolutely great for developers. But it turns out that it's actually really great for the cloud as well. And so now it's sort of the runtime which underpins IBM's cloud offering as well. But it also turns out that what's great for the cloud is great for IoT. So one's, this end of the spectrum, and the other end's this end of the scale spectrum, but the requirements are the same. So you need density, whether you've got a small device or a huge mainframe with lots of servers on it. You need to be able to pack a lot into the space. So you need, again, small download, small footprint. And you need a good deal of elasticity as well. So you need to be able to, instead of getting what you get, you need to be able to say, I only want what I need, and everything else I'm going to throw out. OSGI, it's most typically used now in things like IDEs and application servers, these really big systems. But it actually started out, and there's still a huge community of people who use it, and it was called the Open Services Gateway Initiative, and it was used for things like set-top boxes and embeddable devices. So there's this kind of nice circularity where it started out for embeddable devices, and then the middle of the market, the sort of the application space, I think has never really taken to OSGI because it brings you a lot, but it also comes with a cost. But at the sort of the big end, like the application servers, you need OSGI if you're going to write a sane application server. So almost all of the application servers have OSGI in their internals. And then the big application servers, because of OSGI, have now become small enough and flexible enough that they can fit in the embedded devices. So it's sort of gone this full circle, and that pleases me. And what OSGI brings that makes this possible is dynamism. So I want to go back to talking about my experiences with the Raspberry Pi now. One of the big challenges that I've had with it as I've brought it around is finding the darn thing, because a computer is only good if you can connect to it. And a Raspberry Pi, normally you'd connect to it by HDMI, which means bringing an HDMI display with you, which is absolutely no good at all if you're traveling. And so instead, you'd SSH into it, but that only works if you know the IP address. And this is sort of a simple thing, but it's one that's taken me quite a lot of grief to work out, which is why I'm sharing it. So normally you'd SSH into it, but only if you know the IP address. And so I now finally have a workflow for Pi and Zeek, which is I have my Raspberry Pi and I have my laptop, and I have no idea how to get them to talk to each other. So what you need is an Ethernet cable. You can do it. There is a debug cable for all of these machines as well, but an Ethernet cable is easier to get hold of. You have it configured to use DCHP. You share the network from your computer from Wi-Fi to Ethernet. And then once you've done that, you can use NMap to find everything else on your local network. That will be a very small list if you look at the network, the Ethernet network, because only the Pi is on there. And then you get the IP address of the Pi, which is an amazing thing and has saved me lots of grief. So I'm going to talk now a bit more about my demo. I've done a few Internet of Things demos, but one problem I find is that I think it's such a cool technology, but then the demos can be a bit static because it's a very small thing and it's stuck at the front of the room. And so I wanted something that was a bit more easy for people to interact with. And so I thought, I'm going to do textile engineering, which is my fancy way of saying sewing. And I came up with this, which is a sphere. And it's the Websphere Sphere. And I believe, no one has contradicted me, I believe this is the world's first cuddly application server. I showed it to my mum and I said, look, isn't this cool? Look, it's an application server that you can throw around the room. And she said, why would you want to do that? And at this point I concluded that, there was just a gulf between us that could never be bridged, because clearly it was obvious why you'd want to do this. So I wouldn't dream of doing a product pitch because that's not cool and you're all paying to be here. But you may notice a little bit of a resemblance, or actually you may not notice a resemblance. I was aiming for the logo, but it didn't come out looking quite the same. It was kind of a little bit lumpier, and you'll see that especially when it comes round. And I know what I did wrong. But the one thing about working with hardware is that with software, when you get it wrong, you just change the problem line. With hardware, or things like textile engineering, you have to start from scratch. And so this is really expensive and a bit soul-destroying. So it did make me grateful for what we have with software engineering, which is that when we get it wrong, we just change the one character, and we don't actually have to do the equivalent of typing the whole thing over again. So what we have here is a computer case. a slightly unconventional computer case. And I have a small pcDuino, which is with a bunch of sensors, and the pcDuino is running WebSphere Liberty. And I wanted to make sure that I could see from the outside of the ball what was going on. And so I have these really quite groovy LED sequins. And so you can see one of these here. You're supposed to be able to see that one of them is lit up. But one problem I found with a lot of IoT things, it's the world of hardware again. They're so flaky. And we think software is flaky, but we haven't tried, not compared to hardware. So, this is a wiring error. Nope. Nope. We'll come back to that. It does lead me neatly to my next slide, which is on soft circuits. This is incredibly cool technology. You can get conductive thread to make flexible circuits. It's so cheap. It's stainless steel. It's spun. It's 6 pounds. It's really cool. You can solder it. You can sew it. One challenge with this is how to make a connection between the hard things and the flexible things. I Googled a lot, and there was lots of suggestions, and none of them seemed quite right for my application. And so I came up with these, which is that I took a normal jumper lead, I stripped the ends off, and just then twisted them around. These are hooks and eyes for holding coats together. And so I was really, really pleased with this, until I discovered some more hard facts about the physical world. So here we have sort of reminder of basic electrics. So we have our circuit, and this is a short. And when you have a short, very bad things happen, particularly if you happen to have a computer in the circuit that got shorted, because then the computer is not a happy computer. I've shorted my pcDuino many times. Every time it powers itself off, as you'd expect, but luckily it hasn't actually fried itself, but I think it's only a matter of time. But the other issue you have with physical connections is that you can get loose connections and then nothing works, which is, I think, what's afflicting me at the moment. And a loose connection is particularly irritating if you have a sealed unit, which is what we have here. So when I get a loose connection somewhere inside the ball, I have to take the whole ball apart. And that has happened to me twice with my soft hard connections that I was so pleased with. So what you have here is, I thought I was going to have to do a real detective hunt to find my loose connection, and actually no. Oops. I don't know if you can see, but that brown wire is supposed to be connected to that, and you can see it is in no way connected. It just completely snapped. So I had to put lots of electrical tape around everything for strain relief. Another really useful IoT technique is the world of shields. And so shields are daughter boards, but they have a bunch of advantages. So one is that they rearrange the pins, and that can make it a lot easier to do things, connecting sensors, connecting that kind of thing without needing breadboards, which are a bit of a pain. Sometimes they give you extra functions, so things like Wi-Fi shields give you electrical function. If you are foolish enough to take your pcDuino and stuff it in a ball and throw it around the room, then it gives you a great deal of mechanical protection as well, and some heat dissipation. So with all that, let's have a look now and see if we can make this work. So I actually have 2 batteries connected to this thing, because I have the battery that's strong enough to power the LED lights, and I have the battery that isn't, only since the LED lights aren't working anyway. We can ignore that. And so it's always an adventure trying to coax this thing in. I'd had so many problems with my Raspberry Pis, and I saw the pcDuino. I thought, wow, everything is on one board. That's going to be so awesome. I'm going to have incredibly robust demos. And it's been even flakier. So I think there's no winning. But this is the horrible moment of truth now, where who would like to try and catch the ball? Everyone puts their hands down. Right. Hooray. So you can just pass it around the room, and while you're passing the ball around the room, we'll have a try to connect to it. So there's I wanted to make it able to be passed around the room, and that required a lot of padding, but of course there's an incompatibility between padding and what computers do, which is generate heat and require heat dissipation. So I've got temperature sensors attached to it, and that's very sad. Can we let's try, yeah, let's have it back. I got the IP address when it was upstairs, and so it might be on a different IP address, or it could have just turned itself off. So we'll coax the little guy back out. I think with all of these things, the one lesson I'm learning is that onboard is definitely the way to go. So you can see I've still got like an absolute, even though I got onboard Wi-Fi and onboard battery-ish, there's still this absolute mass of connectors, and they all go wrong. They've got on the Bluemix stand, they've got these really nice Texas connector microcontrollers, and they've got integrated sensors, so things like temperature and light, which are the sensors that you'd probably want, and integrated Wi-Fi as well. So it is up. 10.20.12.188. Aha. So that is taking a while, but I think it is going to come up. I hope. Right. Now we can throw it around the room again while we wait. You get to catch it again. I'll be very sad if it doesn't come up, having just retrieved it to get the IP address. Oh, is the IP wrong? 10.212.188. So we can try. Oops. So it's kind of sad that we're not actually connecting to the application server running on the ball as it's being thrown around the room, but instead we're debugging the application server running on the ball as it's being thrown around the room. That doesn't seem very happy, does it? I think we are on a slightly different subnet, and that's what's going to cause problems. So I'll have to get it back again. Actually, I've changed my mind. I'll sorry. You hang on to it, and we'll try a different approach. So one thing this has definitely illustrated is it's IoT, but it's only kind of IoT, because we have a thing, and the thing is embedded. It's very embedded, and it's very, very, very embedded because you possibly didn't expect WebSphere to be embedded. We have network, but as we've seen, we don't quite have internet because something can connect to it, but this laptop can't connect to it. And certainly people outside this building couldn't connect to it. And when we think of IoT, we really think of machine-to-machine communication. So that's an important part of it. And definitely a prereq for that is some kind of communication. There's lots of competing standards for machine-to-machine, but the one that's really, I think, got a lot of popularity is MQTT. And so I have a revised architecture, which is that I have an MQTT broker on the sphere, and I've taken my application and I've uploaded it to Bluemix. And it's actually the exact same source code, which is kind of cool. And IBM IoT Foundation, which is an MQTT broker that integrates with Bluemix, is used to handle the communication from the sphere to this. And so hopefully, even though I can't connect to the sphere can connect to the internet, and we can make that work. So Bluemix implements Cloud Foundry, so I use the Cloud Foundry commands to connect to it. And I can take my application and I can push it. And what this does is it packages my application into a very portable form with all its dependencies, and then it uploads that to Bluemix. And so if I go to bluemix.net, I should see an application called Sphere appearing. Hooray. And so it's stopped at the moment because it's in the process of being uploaded. And I can add services. And Bluemix is providing platform as a service, and so one of the things that's a part of that platform is the application server, obviously. But the real pain in standing up servers isn't just the server, but it's all the services that go with them, the databases and that kind of thing. And so these are much more simple to stand up. So I need an SQL database. Somewhere down here. When I think they need to revise their UI a bit, because when Bluemix started, it had a small number of services, and now there's a lot of services, and they fill up a page. So what I'm doing is I'm creating a database, and it's going to stand up a database, and then it's going to provide a configuration to my application so that my application can automatically connect via JPA to the available database, which is kind of cool. While this is doing that, I'll also stand up the Internet of Things side. So the service at the very bottom so I'll just confirm that it is actually up. Ooh. So this is more or less what I'd expect, which is that I've pushed a youre up, but I haven't yet done the database because that's in the process of happening in the background. And so if I click restage, it will restart my application and it should be connected to the database. And I can do a similar trick for the Internet of Things, and then I can configure an MQTT broker to connect to the sphere. And with that, I can do a couple of things. It's two-way communication, so I can get the sensor data from the sphere, and I can also push out so that every time I access an application via Bluemix, the lights flash on the sphere if the lights actually had enough power. So I'm out of time, so I'll leave it here. But I'm happy to take questions, and I'm also happy to do the last 2 minutes of my demo if you'd like to come up and talk to me afterwards. So thank you very much. I hope you found this useful. And as I said, I am happy to answer questions.